All right. Here, see if I can minimize this. Am I going to minimize from you? There it goes. All right. So here is your assignment 2-2. The ballerina assignment. 2-2. So assignment 2-2, you can put down your name and so on there. Let's start with number 1. So in number 1 it says use the graphs to find these limits and then answer infinity or negative infinity from looking at. So for number 1, I'm just going to write this limit like this. The limit as x approaches 2 from the left of 1 over x minus 2 squared. And the other one is from the right of the same function. And then to use infinity or negative infinity, because you could use, just does not exist, because there's no way to approach infinity. Here we go. So in number 1, when I look at it, at 2, and even though it's not labeled, the asymptote is at positive 2. So from the left, so even though you don't see it, this is 2 because the asymptote is at x equals 2. From the left of it, where is it going? From the right, where is it going? And both answers would just simply be infinity. So to the right and to the left. So you could say that as a two-sided limit, the answer would be infinity. So you could say that the two-sided limit does exist. But here's one-sided, and the answers. Number 2, the limit as x approaches 2 from the left. Now it's just 1 over x minus 2, or the limit as x approaches 2 from the right of 1 over x minus 2. You're given the graph. So you can see left, minus sign is the left. So where's the graph going left of the asymptote? It's going down forever. So the left is negative infinity, and the right is positive infinity. So as a one-sided limit, it exists this way. But there is no two-sided limit here because they don't agree. Here, there is a two-sided limit that exists. Number 3. Number 3 says find the asymptotes and classify them as even or odd. So let's do that and what that means. So we have f at x equals 1 over x squared. So the step 1 is there anything removable or factorable to remove first? Because I have to remove the wholes first before I know what the asymptotes are. This is prime. There's nothing to remove. Then look at the denominator. What x value makes that undefined? Or what x value makes the denominator 0? And the answer is 0. So at x equals 0, there's an asymptote. So if you plug in 0, it's undefined, and on a graph would be a vertical asymptote. Look at the exponent for that. And the exponent is even. So we say this is an even asymptote. And an even asymptote means on both sides of the vertical asymptote, they both go up or they both go down. In this situation, both would go up. You wouldn't even have a negative answer. So both sides would go out to positive infinity. So we're looking at the exponent, and we're looking at the 0, and then we're writing it down. Number 4. So step number 1 is there anything removable? And I want you to notice the x's are removable. This can be written as 1 over x minus 1 squared. The x's create a hole in the graph. What's left over that's not removable are vertical asymptotes. So we have a vertical asymptote where? So what makes this 0 in the denominator? If you made x subtract 1 equal to 0 and solved it, or some math intuition, what value for x makes that 0? So that's positive 1. How do I know if it's even or odd? Look at the exponent. Because the exponent is even, it is an even vertical asymptote. Again, that means on either side of the vertical asymptote, they both go up or they both go down if it's even. If it's an odd asymptote, on one side it goes up and on the other side it goes down forever. Number 5. Here's an example where I need to factor. So I'm just going to factor it right away. X squared X squared subtract 4 is the difference of squares, so I'm just going to write it in factored form. Is there anything removable? No. So this is prime. So then when I look at the denominator, where are the two vertical asymptotes? So what makes the denominator 0? -2 and +2. So both positive and -2 are the vertical asymptotes. Look at the exponent. So don't look at the number 2, but the exponent you don't see. And the exponent you don't see for both of them is 1. It's an odd number. Both of these are odd vertical asymptotes. That means for each asymptote, it would go up in one direction and it would go down in the other. Number 6. And again, I'm just going to factor right away. So in the numerator, you have x. In the denominator is factorable. So two numbers that multiply to -2, and they combine to -1. So that would be -2 and +1 if you'd factor it. Is there anything removable? No. So these are non-removable. Those are vertical asymptotes. What's one vertical asymptote at +2? And the exponent is odd. The other one is -1. And again, the exponent is odd. So for both of these asymptotes, it would go up in one direction, and then on the other side, it would be going down. So they'd be going in opposite directions if they're odd, or in the same direction if there's an even exponent. Number 7. Without using a calculator, find these limits. So the limit as x approaches 3 on the left of x over x minus 3. So if I want to know this, I kind of need to have an understanding where's the vertical asymptote. So what makes this 0 here? There's nothing removable. And it's at 3. So at 1, 2, 3, we have a vertical asymptote. So as x approaches 3 from the left, what's happening? Well, to the right of 3 would mean if you plug in a number bigger than 3, I want you to notice that the answer is positive. So if you plug in a number bigger than 3, we have a positive answer. For a vertical asymptote, it's either going to go to infinity or negative infinity. So knowing that it's positive, the right side is going up forever. Knowing that the vertical asymptote where it comes from has an odd exponent means the other side must be going down forever. They go in opposite directions. So because of the minus sign, where is that going? And the answer is negative infinity. Number 8 has a question without a plus or a minus sign to it. So I'm just going to write number 8 right here. So the limit as x approaches 3 of x over x minus 3, we already have the graph. Notice they're going in opposite directions, so we can't even say infinity or negative infinity because they don't agree. So as it approaches on either side, they must agree for the limit exists. They don't agree, so the only correct answer here is they do not exist. Number 9. In number 9 and 10 are the same function. So the limit as x approaches 1 from the right, and I'm going to factor this right away. So the denominator, you'd factor out an x and have x minus 1. I'm going to do a quick little graph here so I can see it. Now I want you to notice we have a hole here and an asymptote. Do you know where the hole is? Do you know where the asymptote is? So what gets removed is x. Make it equal to 0. There's a hole when x is 0. Where's the asymptote? Well, what's left over here, so I can remove the x and have 1 over x minus 1. So the hole got removed, but the asymptote remained. So there's an asymptote at positive 1. So 1 from the right compared to the left. So if I plug in a number bigger than 1, I want you to know it's a positive answer. And then on the other side, it would go in the opposite direction if it's less than 1. So for the right side, what's happening? And again, it's going to be 0, so it would look like this if I would want to graph it. But I'm looking here, what's the behavior to the right of the asymptote? And the answer for number 9 is positive infinity. For number 10, that uses the same function, notice that at first, if you try to plug in 0, it is indeterminate. But once you simplify it down, 1 over x minus 1, you can plug in 0 and get an answer. So when you plug in 0, get 1 divided by negative 1, and you get to evaluate the limit that way. Number 11. So 11 and 12 look similar, but they're not. So they're not the same. So the limit as x approaches 3 of x plus 3, and then the denominator is, and I'm not going to write it squared. I guess I could write it squared in this case. Let me write it squared. So if I factor this, you'd have this. And I want to know what the value is x approaches 3. Now, it might be helpful to have a graph in terms of understanding it, or we're going to think through it mentally a little bit here. So first of all, when x is 3 and I plug in 3, I can see that it's undefined. You could write down the answer does not exist because it's 6 over 0, undefined, doesn't exist. Or you could also write down because of the even exponent on both sides, they're going in the same direction. Now, if I plug in a number bigger than 3 or smaller than 3, because of that too, both answers are going to be positive. Now, it will be negative eventually once you plug in a number that is what, negative 4 or smaller than negative 3. But right around positive 3 on both sides are going up forever because of that even exponent, and you can write down the answer for number 11 as infinity. 12 looks similar. So the limit as x approaches 3, but instead of x plus 3, it's x minus 3. So that's why I'm doing this, is I am expanding it. So instead of x subtract 3 squared, I expand it so that I can remove x minus 3. But the thing is, x minus 3 is not completely removed. So even though I removed, I can only remove 1, but 1 remains. That means there's still an asymptote at x equals 3. So, but now look at what's happening at that asymptote. So at 3, that asymptote, we have an odd exponent. This is not a one-sided limit. So because it's a two-sided limit for number 12, and it has an odd exponent, that means one side goes up forever, the other goes in the opposite direction. They don't agree at what the direction they're going, so the limit does not exist. Number 13. The limit as x approaches 0 of x squared minus 2x over x cubed. So the first thing I'm going to do here, again, is I'm going to factor. So if I factor out an x in the numerator, I want you to notice the x does divide out with x cubed, but it doesn't remove it completely. It's still non-removable, but what I'm left with is x squared. So now when I look at 0 in terms of x squared, when I plug in a number around 0, so if I plug in positive 1 or negative 1, what answer do I get around 13? So I want you to notice the answer is actually negative infinity. Well, why is that? Well, you do it. Plug in positive 1. That's to the right of 0. You get negative over a positive. Plug in negative 1, and you get a negative over a positive. So on both sides, they're going in the same direction, but they both are going down in this case, because when you plug in, you get a negative answer on both sides of 0. Number 14. The limit as x approaches 0 from the left of 1 over x minus 10. So I want you to notice, again, for number 14, that for 1 over x minus 10, what's happening to the left compared to the right? Well, when I plug in 0, that is non-removable. So at 0, there's an asymptote. So it's either going up forever or down forever. Now it's one-sided. So if it wasn't one-sided, it would not exist. What happens when you plug in a number bigger than 0 compared to the other way around? So compared to the left. And so I want you to get a sense of where it's going. So if I plug in a number to the left of 0, like negative 1, plug it in, is the answer positive or negative? So if you plug in negative 1, which is to the left of 0, the answer is negative. the left side of this is going to negative infinity. Number 15. In number 15, you're given a graph. So find these limits without using a calculator. So 15a is the limit as x approaches infinity of f at x. I could just write it that way. And then the other side, the limit as x approaches negative infinity. These are asking end behavior questions. We did these questions before. These are end behavior questions. So if I look here, what's the right and left behavior? Well, I could count and see it and use the power terms to realize and divide it out. That number, the right and the left, are both going to what number? 2. So the right is going to 2, the left is going to 2. So both of these, the end behavior is 2, and that's where it's doing. So what's the limit as x approaches infinity of f at x? 2. What's the limit as x approaches negative infinity of f at x? 2. This is like saying, what is the right end behavior? This is what's saying, what's the left end behavior? Number 16. Again, it's going to be off a graph. Even if we didn't have a graph, we could do this, just understanding end behavior. So, and we'll be doing that 18 and on. So the limit as x approaches infinity of f at x. B is the limit as x approaches negative infinity of f at x. Okay, so let's look off the graph. I can tell already because the bottom is more powerful. The right end and the left end behavior is 0. But look off the graph and you can see the right end and the left end is approaching 0. Done. Number 17. A little bit more challenging of a function, but you can still do it. So for 17, you have the limit as x approaches infinity of a different f at x. And for b, the limit as x approaches negative infinity of f at x. So again, what's the right end and what's the left end behavior of that function? So I'm just going to follow the graph and realize the right end is going to positive 2 and the left end is going to negative 2. Number 18. So 2x plus 5. So sorry, the limit as x approaches infinity of 2x plus 5 over 3x subtract 4. This is asking for end behavior. So the limit as x approaches infinity, that's the right end. Just use the power terms. That's 2x over 3x. And then that simplifies to just 2/3. And once it's a constant, that is the answer. So the right and the left end are approaching 2/3. Number 19. The limit as x approaches negative infinity. So remind yourself that's left end of 1 minus 5x cubed and then 10x cubed subtract x squared. So step 1, identify the power terms of the numerator and denominator. So in the numerator, the power term is negative 5x cubed because it's the term with the biggest exponent. The sign matters. And in the denominator, it is 10x cubed. Again, this is going to simplify to a constant. So the x cubes divide out. If I wanted to, I could simplify it and then realize that once you have no variables, the limit is what that constant says. So the right and the left end are going to negative 1/2. Number 20. The limit as x approaches infinity. And we have x, 2x minus 1 squared. We've got to be careful with these because we need to know the power term. And sometimes we have to expand it with the exponent to understand it. So first of all, it is the right end. Next, identify the power term on top. And you're going to have to do some algebra here. So I need to realize that when I multiply this out, what's the biggest term? Not all of them, but what's the biggest, most powerful term? And when you square 4, what you're left with is 4x squared. I'm going to do it in 2 steps. So 2x squared is actually 4x squared. There it is. And we still have an x in front. How about here, that's an x squared, just the most powerful term. And then I'm going to reduce that down to get my answer. So what things can I reduce down? X squared divides out, x divides out, and I'm left with 4/3. And the limit of a constant is just that constant, and it's done. Number 21. The limit as x approaches negative infinity. That's the left end. Sometimes the right and left agree, and it doesn't matter the end because both ends are going to the same number, and sometimes not. So in 21, we have 4x squared plus 3 over 2x. So identify the power terms. So here I have 4x squared. Down here I have just 2x, so that's the power term. Then can you simplify it? So 4 divided by 2, that's 2. X squared divided by x, well, that's just x. I'm actually left with no variable in the denominator. It's just 2x. And when I think, what is 2x? I'll draw it. It's just a line. In what direction is that line going? Well, it's a positive slope line, so it's going up to the right. And so the question is, the right end behavior. Well, you can see that the right end is going to, for 21, or does it say negative infinity? The left end. How about this one? That's the left end. Where's the left end going? And the answer is negative infinity. 22. The limit as x approaches negative infinity. Now this one's going to be a bit of a challenge, but you are up to it. X over the square root of x squared plus x. So again, the power term. Now, in order to find the power term here, x is the only term, so it's the most powerful. Here, I need to do the square root of x squared. But because it's a quadratic, and it's like solving a quadratic, the answer is positive or negative x. So when I do this and then figure it out from the left end is the negative answer, and the right end is the positive answer. So this positive is not what I'm looking for. I'm looking for the left end, which is negative. And then when I divide this out, you can see the left end is going to -1. If it was the right end, you would keep the positive and not the negative, and the answer would have been +1 for the right end. In fact, if I look at question number 23, I'm not going to write it all out. I just told you the answer for 23. The same question, but the right end, the answer for 23 is +1. 24. The limit as x approaches negative infinity, and we have 2 minus x and the square root of x squared minus 3. So when I evaluate this, and this is the left end, the numerator, the most powerful term in signs matter, it's negative x. But when I take the square root of x squared, I'm going to be left also with negative x. So it's negative on the bottom because of the left end. So when I simplify this, the answer to 24 is +1. Number 25. The limit as x approaches negative infinity of 2x squared subtract 2 over the square root of x to the 4th. And again, it's the left end that I'm looking at here. So the power term in the numerator is 2x squared. In the denominator, take the square root of x to the 4th, and it's x squared, but it's going to be negative x squared because it's the left end. So when I simplify this, that's why the answer is -2. It would be +2 if it was the right end. Oh, then it says use a calculator to find the right end behavior of that. So let's do that. So for number 26, I'm going to use Desmos. So you can press pause and open up Desmos whenever you want. The limit as x approaches infinity of x to the 5th e to the -x plus 2, and figure out what's happening here. So in my head, as the numbers get bigger to the right, so if I put in 1 billion, this will take over this. The negative exponent means it goes in the denominator. That means the same as x to the 5th over e to the x plus 2. They're equivalent. And this is going to take over, meaning this is more powerful. Meaning, and we'll show it on the calculator too, if I separate this to evaluate the limit, recognize that this, because the bottom is more powerful, the right end behavior is 0. Here, it's a constant, so it's 2, so that entire answer is 2. But let's look on the graph and what that would look like. So, x to the 5th e to the negative x plus 2. So x to the 5th e to the negative x plus 2. What is the end behavior as we look here? Make sure you don't make a liar. I mean, no, it's 2. So what did I do to type this in wrong? X to the 5th e. Maybe it didn't like that e. Maybe I have to use the e. Maybe I gotta use this e. Or am I missing where e is completely on here? I'm assuming that that's okay, right? Times e to the negative x. There it is. Ha! I didn't expand further enough. So, notice at first, this graph goes way up. But then know what happens? It eventually comes down again. So the end behavior doesn't go up forever. But I had to expand out to be smart about it. So if I zoom in here in terms of the end behavior, what number is it getting closer and closer and closer to? Notice that it's getting closer and closer to 2. So this right end behavior here, look at that answer. The y coordinate says you plug in fact, it won't even Now, what's the left end behavior? Well, the left end behavior, if you're asked for it, where does the left end go? You can see the left end behavior goes to negative infinity. So as you put in negative values, x to the 5th is a negative answer. E becomes a negative times a negative, becomes this huge negative answer plus 2. But anyways, we're looking at the right end behavior, and you can see the answer is 2. Graphically and algebraically, I showed you. All right, 27. We're going to go to question number 31 on this video. Then I'll do a second video, and you should take a break. All right, f of x. And what am I doing? The discontinuities. I love discontinuities. Now, the denominator, I'm going to factor right away. And then I look at the denominator. So where are the discontinuities? So look at the first one. What makes this not continuous if this is 0? So what x value? So we have 1 when x equals negative 2. Is it removable or non-removable? Can x plus 2 be removed? Yes. There's a hole there. So this is removable. Where's the other discontinuity? At positive 2. Can you remove x subtract 2? No way. It gets left over. So this one is non-removable. It is an asymptote. So negative 2 is a hole. It's removable. That means the limit exists. At positive 2, it's non-removable. That means the limit does not exist. The limit exists as it approaches negative 2. The limit does not exist as it approaches 2. Removable, non-removable. 28. Here we have a step function. So what have we learned about these step functions? Integers, there's jumps. So what x value creates integers? So at every multiple of 3, there is a non-removable because the limit doesn't exist there. So every multiple of 3, it creates an integer, which then creates a jump in the graph. And it's non-removable because at a jump, the limit does not exist. 29. Here we have a piecewise. So we have x squared and 2x minus 2. The top is valid when x is less than or equal to 2. The bottom is valid when x is bigger than 2. And the question is there any discontinuities here? Well, x squared is continuous. 2x subtract 2 is continuous. Those are polynomials. But what happens when you plug in 2? Is there a jump, or do they equal the same thing? So when I plug in 2, I get 4. When I plug 2 into the bottom, I get 4 take away 2, which is 2. So at x equals 2, we have a non-removable. Because there's a jump, discontinuities, if I can spell that. So at x equals 2, there's a non-removable discontinuity. Because when you plug 2 in, it creates a jump. It goes from 4 all the way to 2. Number 30. Another piecewise. Different. X squared, 2x. X is less than 2. X is greater than 2. These have no discontinuities. What makes this one different? Well, for number 30, if you plug 2 in, the answer is 4. If you plug 2 in, the answer is 4. Because they have the same value, there is no break or jump in the graph. So there are no discontinuities for this piecewise. Why is there one here? Because when you plug 2 in, you get 2 different answers, which creates that jump in your graph. All right, last question for this video. Number 31. Again, the discontinuities. You have the absolute value of x plus 2 over x plus 2. Are there any discontinuities here? And look at the denominator. So at x equals negative 2, we have a discontinuity. And for this type of function, absolute value over here, when I plug in a number bigger than negative 2, the answer is positive 1. If I plug in a number smaller than negative 2, like negative 3 or negative 4, you get an answer that's negative 1. So on one side is positive 1, and then it jumps to negative 1. So this is non-removable because the limit does not exist. So at negative 2, so if I graph this, right here, at negative 2, the answer would be positive 1. And then if it's to the left of negative 2, the answer would be negative 1. They both would be holes. Exactly at negative 2, it doesn't exist. So to the right and to the left, and then you can see the jump that creates. So for number 31, it is a non-removable discontinuity at x equals negative 2. All right, Mr. G Math, over and out. I am so proud of you for doing your work and working through this. Distance learning the whole bit. Until next time, and I'll do part 2 right now. But give yourself a break.